Hey guys, this is chapter 14.2, order paths and circuits, and let's get started. So, a path that passes through each edge of a graph exactly one time is an Euler path. We know that already. That one's not hard. Alright, next question. Oh, wait. A circuit that travels through every edge of a graph at once is an Euler circuit. Okay, that's easy. Okay. A connected graph that has at least one Euler path but no circuit has exactly two odd vertices. Remember that, guys. That's the Euler theorem. A connected path that has at least one Euler circuit, which by definition is an Euler path, if the graph has no odd vertices. And the Euler circuit can start at any vertex. Okay, so remember the theorem. The theorem states, so by definition, a path is just if you cross every edge once, right? Every edge is crossed once, you have a path. But if you happen to start at one vertex and end up at the same vertex, that path is also a circuit. That's the idea. So every Euler circuit is also an Euler path. And that means it has no odd vertices. That's what the theorem holds, and it's true. And of course, that means that you can start anywhere. Any even vertex will be fine. A connected graph has no Euler paths and no Euler circuits means it has more than two odd vertices. Okay. Remember, odd vertices come in pairs. So Euler's theorem enables us to count graphs odd, whatever. A procedure finding such a path and circuits is called the Flory's algorithm, right? When using an algorithm, faced with the choice between edges to trace, choose the edge that is not a bridge. You do not want to cross bridges. Okay, you don't want to disconnect parts of the graph. Let's see. Every Euler circuit is an Euler path. That is true. Not every path is a circuit. Okay, you can have a path. Remember, a path doesn't necessarily start and stop in the same place. But a path just means you crossed over every bridge once. Or the circuit means you cross over every bridge once and you started and stopped at the same place. So this is true. The Euler circuit and Euler path are paths that travel to every edge once and only once. Okay, so it's A. Alright. Or every Euler path is also a circuit. That's false. Because you have to start and stop in the same place to be in a circuit. And that's not necessarily the case for a path. So it's a false claim. It's probably this one, longer one. Let's read it. The statement is false because both Euler circuit and path are traveled through edge once, only once. Euler path also begins on the same vertex. Euler path, Euler circuit does that. Euler path does not have to begin. Yep, it's B. I figured it's a longer one. Let's continue. All right, let's look at this one here. So it says here, we're going to look at this particular path, and we're going to see whether it's a circuit, Euler circuit, Euler path or not. Let's see. So first of all, you know what? Before I even go through this path to see if this even works, I'm going to see if it's even possible. So what if it's not even possible? Then we can just automatically guarantee it's neither, right? So F has 2, A has 1, 2, 3, 4, E has 2, 1, 2, 3, 4 for D, 2 for C. Okay, everything is even, so either is possible. You can either say it's a circuit or it's a path. You can say one or the other. So let's see. You know it's possible, but let's see if this works. It's asking to determine if this is one of it. F to A. I have to actually draw this. So let me do the marker thing. Okay. F to A. There's 1. A to D. D to E. Then E to A. Then B. Then D. Then C. Then B. Oh, what just happened? An Euler path or circuit is possible, but what just happened? It's completely forgot to go over FB. Just completely skipped it. So it's actually, this particular path is not an Euler path or an Euler circuit, right? So the path described is neither an Euler path because at least one edge is, it's not why. It didn't travel over an edge once. It's this one probably. Because not every edge is traveled once. It's B. Oh, I gotta get rid of the drawing. Clear. And put B. Okay. Simple stuff, right, guys? Again, we're going to test it. Again, I'm just going to, before I even bother a minute, just count very briefly the edges. 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 2. Okay, everything has even, so it could be any. Let's see. I'm going to put the drawing thing. F to A to D. Let's see. F A D E A E A B D C B F. Oh, okay, it worked. It's an Euler path, a circuit. Sorry. So we definitely know it works. Let me clear it. It started and stopped at F, and it goes to every edge. So let's see. It's it is said neither. It's an Euler path, but not a circuit. Not true. It's an Euler circuit because it does not. Nope. It's probably F. The path describes an Euler circuit because it travels every edge of the graph at least once and begins and ends the same vertex. So it's F. Excellent. And you guys don't put the same answer I'm putting, guys. Your questions are different. Make sure you answer your questions. It says here. Let me look at the again edge. Same question. Let's see. F is 2. E is 2. D is 1, 2, 3, 4. 1, 2, 1, 2, 3, 4, 1, 2. Okay, so they're all even, so it's all possible. Notice how it starts in A, ends in C. So right there, it can't be circuit. We can get rid of these as well. So we have to draw it out. Oh, wait a second. Well, yeah, we have to draw it out. It may not be done correctly, so we have to see. So A goes to B, and then A, and then D, right? And then F, E, and then B, D, C. Ah, it didn't finish. It skipped CA. So it's actually neither because it did not travel through every edge. Okay? So it just completely forgot to skip. It went over. It forgot an edge. Let's see this one here. A graph is given to the right. Okay. Explain why the graph has at least one Euler path. Well, let's see. A has 3, B is 3, that's 2 odds right there. E has 4, C is 2 and 2. Okay, so there's exactly 2 odds. So it has an Euler path, we know that. Okay, so we got to figure it out. So let's see. We're going to start at one of the odd ones. So we can start at, does it tell us particular? Oh no, it actually tells you where to start. It says start at A, so we're going to start at A. Because technically we're going to start at B, right? B is also odd, but they want you to start at A. With E as the 4th and 7th. So then that means don't go to E. So we gotta go down to, I guess we gotta go down to B. So let's put B. And then we're gonna go to C, right? And then you're gonna go E to the 4th, that's the 4th one, good. And then we're gonna go, so I went around. I'm gonna go around again to DA, and just put D. Oh yeah, D is the 5th one, okay. A should be the next one. And now, so remember, I started at A, went to B, I went to C, E, D, I went in a circle. Now I'm going to go to E and then end up at B. So E and B. This should work. This should do it. Yep, there you go. Explain why it has at least one Euler circuit. Well, that means that there's no odd vertices. So it's this one. I don't have to even bother. Then it can ask me to do it. Right, and circuit starting with A. Okay. I like this. I like to write it better. So let's see. Let me go like this. Let me go A, B. Go back to A. Yeah, I'm going to do that. It's going to be A, B, and then, do I have to put commas? I have to put commas. Sorry. B, and then I'm going to go C. No, I said I'm going to go back to A. Then I'm going to go to E. Then I'm going to go to B. And then I'm going to go to C, then E, then D, then A. I think I traveled everything once. Let me double check. I actually trace this way. So A, B, A, E, B, C, E, D, A. Yep, I did everything perfect. It looks good. So let's check. Excellent. Whoa, that's pretty cool. So let's see. Explain why this graph shown has no Euler path and no Euler circuit. I don't even have to look at that graph. It must have more than 2 odd vertices. Let's see. It has more than 2 odd vertices. It's the only answer that makes sense with the theorem. So we know that. We don't have to even bother with the graph. There's a graph that has 54 even vertices and no odd. That means you can have an Euler circuit. Okay. So let's see. When they're all even, you can have a circuit. This is because it has no odd vertices. There's something that's 98 evens and 2 odds. There's your Euler path. Okay, because it has exactly 2 odd vertices. Okay, that's pretty easy stuff. You have 60 even and 8 odds. It's neither. Can't have more than 2. Why? Because you can't have more than 2 odd vertices. That's a bad thing. Okay. Let's see the next one. Determine whether the graph is Euler path. Let's see. 1, 2 for C, 2 for A, 1, 2, 3, 4 for D, 1, 2 for B, 1, 2, 1, 2, 1. Everything has 2. They're all even. So it's an Euler circuit. And then if the graph is on a path or circuit, use trial and error. Oh boy. And it says here, excuse me, the first vertex is G. They want you to start with G, which I can type it. And the third is A. So if I start, where's G? G is here. It has to go to D and then A. There's no other way. So D, since the third has to be A. Okay, so G, D, A. I have to go to C, I have no choice. And then I gotta go to F. And then I have to go to D. And then B, I'm running out of little choice here. E. Wait. Darn it, I think I missed this. So let me go put it back. So let me make sure I got it. So G, D, A as third. Yeah, and then C, F, D. Now I started at G, D, A. So I already crossed here, so I have to go to B. That's what I say, yeah. So I gotta go to B, then I gotta go to E, and then I can finally end up back at G. Excellent, that should be it. That should do it. Alrighty. So determine if this is a path, circle, whatever. Let's see. A is 2, C is 1, 2, 3, 4, 5. Okay, C is odd, so let's find out. Let me look at B. 1, 2, 3, 4, 5. B is odd. 1, 2, 3, 4. Oh, there's more than 2 odds. So it's neither a circuit nor that, and it's a if the okay, I guess you leave it blank. You can't really do it. Yep. Okay, I was wondering. I have to put something there. I guess not. All right. So. Oh wow. Okay. So remember, there's 2 streets. So there's going to be from this vertex to this vertex. There's 2 bubbles. That makes sense. 2 bubbles here. Okay. I think it looks like it's this one. It can't be this one. B, because there's houses on both sides. It looks like it could be A. Let's see. It's not this because A connects with B twice. It doesn't connect to B twice. This one's saying A connects directly with. So here's A, but what? I don't know what this point E is. This is a weird point. Yeah, it's not on the graph. It has to be A. A is the only one that makes sense with the model. What's the question? Use the graph to determine the carrier per intersection, deliver, blah, blah, blah. Okay, so is this possible to deliver everything going over once basically? So let's see, A has 1, 2, 3, 4. 1, 2, they all have 4, I think. 1, 2, 3, 4, 5, 6. So 6, 6, 4, 4. Yeah, they're all even. Yep. And it's going to make me do it, isn't it? Well, it definitely has, since the answer has 2 of these, it has to have 2 going through it. So that makes sense. This makes no sense. A, neither D, they have to go through 2 edges once. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 19. I mean, it makes sense. Let me see this one. 1, 2, 3, 4. Where's 4? Oh no, 4 is down here. It's impossible. Oh wait, I'm dumb. 1, 2, 3, 4, 5. And then here's 6. Yeah, that's impossible. Yeah, well, I was wrong originally, but I was right eventually, right? So this is impossible. So it has to be C. I can't imagine it. Yep, that's what I figured. And I'm not going to worry about this. It says describe where the circuit begins and ends at B. So let's find out. I doubt it's these two. These are too little. So it has to be one of these two. Let me test B. B, A, B, E. Let's see. B, A, B, E, D, A, E, C, D, C. Yeah, it's this one. I traced it, so it should be that. There you go. And that's it for chapter 14.2. Pretty simple stuff. I hope you guys learned a lot, and I'll see you guys for the next lesson. Take care.